Now, what we're going to look at now is we're going to think about how to convert between linear and angular quantities and how to go back and forth between them. Um, if you make a circle with your fingers, that is technically a circle there, right? If you took your fingers and you unrolled them, you could like measure the length of your fingers. So we could imagine a scenario where it's possible that if you had some circle, if you cut it and unrolled it, you'd get some straight line. Okay? This idea right here of cutting and unrolling the circle is the fundamental argument behind converting from angular quantities to linear quantities and linear quantities to an angular quantity. For instance, imagine that you had a perfect circle, and let's actually make a perfect circle. I can actually do this for once. You have a perfect circle. No! There, close enough. I'll never be able to make a perfect circle. You've got a perfect circle here, right? You started here, and I asked you, hey, what's the linear distance of the circle? I.e., what's the perimeter of the circle? Well, if you've been in a geometry class for all of 10 minutes, you have learned what this is. You know that the perimeter of the circle can be thought of as a circumference, which is just 2 pi times the radius of that circle. Right? Like that is something that many of you know and are aware of. Well, instead of calling this a circumference, this is the circumference right here. The circumference is just if you took that circle, broke it apart, and then stretched it and laid it flat, how long is it? That's really what the question is asking. How long is that circle? Or if you took a wheel and you painted the edge of it with paint, and then you just rolled the wheel once, how much paint have you put on the ground? Like how long is that line of paint you've put there? That's all we're looking at here. So when we're looking at these linear and angular conversions, what we can really see is this. That circumference isn't a circumference. It's a linear distance. And we're going to say linear distances, due to the world of math, are written as s, because they could be some curve. And that 2 pi, well, this 2 pi, that is an angle that we have there. And this r, that is the radius of that circle. So what we see is that a linear quantity, s, is equal to an angular quantity times the radius of that circular motion. So what this means is that if we want to, we can say, hey, look, if I have a linear quantity s, that is equal to an angle times a radial distance. If we keep this same argument up, then if I think about, well, if this is an angular, if this is a linear quantity for a position or a displacement, normally we, may have written this as the letter x before. If I'm just saying, look, the linear quantity is equal to the angular quantity times the radius, then that means a velocity is just equal to an angular velocity multiplied by a radius. And an angular acceleration is just equal to, an acceleration is just equal to an angular acceleration times a radius. And that's it. That's all we have there. That's all that matters. All of these look the exact same, and it all comes back to this idea of the circle. And some of these arguments make sense too. And we'll talk about this a little bit later on, but for any of you that are in the band or have ever watched a band, we can't do this right now, but if you imagine for a second, you took a person, you made them the center of a line of people, and then you had a line of people all the way out to the end. If you ask this line of people to stay in a straight line, but to run in an arc so that they now are like this, well, the person on the inside, like this very person here, right at the pivot, like right there, that person isn't actually like moving anywhere. They're just doing that. They're literally just turning, which is super easy. The person in the middle here, well, maybe they're at like a slight jog because they've got to cover this entire arc distance here. But the person at the end, this poor soul, and if it's Max with a tuba, like, oh my goodness, this person's got to book this entire, like, corner. That's a huge amount of distance. Like, this person is covering this entire corner, this entire curve, in the same amount of time this blue person here is doing, like, bloop, that little thing. Okay? So because of this, what we can say is this person's linear velocity out here is the highest because this person is like sprinting. Okay? This person in here, their linear velocity, it's medium. They're like jogging. And this person in here at the pivot, their linear velocity is 0. They're just spinning. They're actually not moving. But all of these people here, they all have an equal angular velocity. Because if we take a look at this, all of them are moving through that 90-degree angle in the same amount of time. And that means when we think about an angular velocity, all of them are moving through 90 degrees, or pi over 2, in the same amount of time. So this is equal for everybody. It's equal for all three of them, which is a kind of a weird thing to think about. But, take your arm and, rotate it like this. Your hand at the edge, your fingertips are moving faster than your shoulder is, linearly. They're covering more distance. For any of you that play sports out there, this is why, if you're swinging like a golf club, the head of the golf club is moving faster than the handle. And you get that kind of whipping action to it. If we've talked about sword fighting at all, if you ever get into a post-apocalyptic world due to the COVID-19 virus and everybody's running around with swords trying to murder each other, if someone swings a blade at you, you actually step into their swing because the tip of the blade's moving very fast, but the interior of the blade's moving very slow because it, by their hand, it's just barely drifting. So you can actually protect yourself like that. So it's just one of those things. All of the linear velocities are different, but the angular velocities are the same. And we see that here in this equation. As you move further out in the radius, as your radius goes up, if that omega here is staying the same, then the velocity has to increase. So this equation makes a lot of sense just based on what we see in real life. And mathematically, it makes sense as well. Okay? Now, there's one other thing that we can write here, but we're not going to need it until much later. A radial or centripetal acceleration. We could say that this is an alpha, but we'll typically write it as AC. And it is actually equal to the linear velocity squared over r. Okay? And this is a little strange how we think about it, but it is, when we see it, it'll be kind of straightforward, but we won't need it until later. Okay. Last little thing that we need to be aware of is what is a radian. Maybe if you're in math classes, you've learned what a radian is, but just as a quick overview, because some teachers actually don't talk about it. If you took a circle of some radius r, okay? If you took this length from here to here and you measured it, that length, if you you peeled it off, you laid it flat, that length is radius r. Okay? It happens to be that for every single circle, if you were to go radius r distances around that circle, it would take you 1, 2, 3, 4, 5, 6, and a little bit to get around the circle. This is why one revolution or one complete cycle of the wheel, this is what is equal to 2 pi. Pi, if you remember, is approximately 3.14. If I multiply it by 2, I get 6.28. Well, 1, 2, 3, 4, 5, 6, and a little bit, the little bit is the 0.28. Okay? So going around in a circle will take you through an angle from start to finish of 2 pi, no matter what. And we call this angle of the angle between one radius of arc length, this is what we call a radian, a rad. So the word radian comes from radius, and something you're probably more familiar with, that one cycle around is 360 degrees. And we're all pretty familiar with that due to Tony Hawk. So that's what we're looking at there. Okay, so these are some kind of fundamental things that we'll be talking about in this unit, doing linear to angular conversions, as well as eventually looking at some centripetal acceleration and understanding what a radian measure is. Okay? But go check out another